Okay, so let's get into drawing these structures. How do we classify our structures? How do we draw them? Everything like that. So, as we said before, a Lewis structure is a representation of covalent bonding. That's a big word right there. Covalent bonding, in which shared electron pairs are shown either as dashes or pairs of dots between two atoms, and lone pairs are shown as pairs of dots. Now, like I said before, I'm going to prefer the dashes for shared pairs and the pairs of dots for the lone pairs, just to make sure we know the difference between bonding and non-bonding pairs. So we have again our structure of water, which we've looked at before. Now, in order to draw these structures properly, we have to follow a certain set of guidelines to make sure that our electrons and our bonds are being represented properly. So we can't just say that we know where the bonds are going to go. We can't just make random bonds places. We have to follow a set of guidelines to draw them. So the guidelines are here below, and I believe in your lecture notes you have to copy these steps down. So copy these guidelines down as we go through them. So our first step is we want to count the valence electrons. Remember, our valence electrons, we look to our group number on the periodic table. That tells us our valence electrons. We have to count the valence electrons of all atoms in the molecule. All of the atoms in the molecule, we have to count up their valence electrons. We then have to draw the skeletal structure with our bonds, or our electron pairs, our bonding pairs, between the central atom and the surrounding atoms. So our central atom, if I were to draw this kind of on the side, is X, and our surrounding atoms would be Y. And our shared electrons, our bonding electrons, are the dashes in between. Okay, so those all those dashes show the bonding electrons. Once we have drawn our skeletal structure and have shown all of our bonds with dashes, we subtract the bonded pair electrons from the total number of electrons that we had overall. The idea here is that every atom is contributing its valence electrons to form this structure. So we think of the electrons going into one big pot, and then we're essentially distributing them evenly throughout the entire molecule because those electrons are being shared. And we're distributing them first as bonds, and then what we'll see is we're then going to distribute the rest as lone pairs. So our next step, after we subtract the bonded electrons from the total number of electrons, okay, we're going to place any remaining electrons as lone pairs to complete octets, and that should be specific to our surrounding atoms. So on the surrounding atoms first. So we're placing any remaining electrons as lone pairs to complete octets on the surrounding atoms first. So that would be like our Ys. So these are our surrounding atoms. Now we also have this thing called duets at the bottom. Duets, if you recall from the last time we talked about the octet rule, this was specific atoms can only have 2 electrons around them. We're going to see this specifically in hydrogen. It will only take on 2 electrons. Okay, so hydrogen will typically only form 1 bond. And this is just because hydrogen only has 1 proton, so it can't balance out a full octet of 8 electrons when it only has 1 proton. That would be far too negative for it, and those electrons would just repel each other and wouldn't balance well with the 1 proton. So hydrogen will only have 2 electrons shared with it. Okay, so after we've completed our octets and our surrounding atoms, we're going to subtract the amount of electrons that we used to do that from our total. If we have any remaining electrons after our octets are complete on our surrounding atoms, we're going to place those remaining electrons as pairs on the central atom. Okay, so that would be the X. That's our central atom. That's this atom in the center. Finally, if all of the electrons are gone and we still do not have octets on all of our atoms, that is when we are going to form multiple bonds, and we're going to do that by moving electron pairs. Now, these guidelines, as they are written, are very useful, but they're not very useful right now because we haven't shown how to use them. So the best way to understand these guidelines and know how to utilize them is through practice. So we are going to practice a lot of structures, and we are going to practice using these guidelines to draw those structures. So let's start out with a few examples. So our first one is CH4. Our first step, we have to count our valence electrons of all atoms in the molecule. So we look to our molecule at CH4. That means I have one carbon. That carbon has 4 valence electrons, okay, because it's in group 4A, so it has 4 valence electrons. We then have hydrogen. Hydrogen has 1 valence electron, but there's 4 of them. So we take the 1 valence electron and we multiply it by 4, okay, because there's 4 of them. So in total, CH4 has 8 electrons that it is going to share amongst the structure. Okay, so we completed step 1. Moving on to step 2, draw the skeletal structure with bonds between the central atom and the surrounding atoms. So how do we know what our central atom is? Well, whatever atom is first is our central atom, and whatever atom is second are our surrounding. There are some exceptions to this. And that would be if hydrogen is first. Hydrogen can never be a central atom. So sometimes we have structures where H comes first. That will not be a central atom. So we typically read from left to right, and that's the way we look at these. So central atom is first, and then surrounding atoms come second. So our central atom here is carbon, and the surrounding atoms are then hydrogens. Now these are Lewis structures, so I'm going to follow similar rules as my Lewis symbols, where I'm going to, represent kind of like a square. I'm going to put those hydrogens on all 4 sides of my carbon square, right? So we put them all on one on each side, okay? And then we're going to connect them to our central atom using bonds. So step 3 then says to subtract the bonded pair electrons from the total. So what that means is I've used up electrons to form the bonds. I now have to count up how many I used and subtract that from the total that I had. So how many electrons did I use to form these bonds? Well, each bond has 2 electrons. So that's 1, 2, 3, 4, 5, 6, 7, 8. I used 8 electrons to form my bonds, so I'm going to subtract that from my 8 electrons that I had total, and I have none left. Since I have no electrons left, I don't follow steps 4, 5, and 6. I don't need to, okay, because I don't have any remaining electrons. The last thing we can do is just double check that our octets are complete. So carbon has how many electrons associated with it? Well, because these are bonding pairs here, those electrons are being shared, and so carbon can claim all of them. So it can claim 1, 2, 3, 4, 5, 6, 7, 8. So carbon has 8 electrons around it. And hydrogen, each hydrogen has 1, 2 electrons. And remember, hydrogen forms a a duet, so it will only take on 2 electrons. So our octet for carbon is complete, and our duet for all hydrogens is complete. So our structure for CH4 is C with the 4 hydrogens around it, each with a single bond. Okay, let's do another one. Let's follow our steps for our next example. Our next example is CH2Cl2. So that's our compound. We want to then draw its structure. So our first step says to count the valence electron of all atoms in the molecule. So we have to count our valence. There's 1 carbon. Carbon has 4 valence electrons because it is in group 4. There are 2 hydrogens, and each hydrogen has 1 valence electron. So we just take that 1 and multiply it by 2. Finally, we have chlorine. Chlorine has 7 valence electrons because it is in group 7, or group 7A. But there's 2 of them, so we're going to multiply it by 2. Okay, so now we have to add that up together. Feel free to use your calculator. It is always fine to use calculators on these simple types of math because you never want to be missing electrons. If we add up our total number of valence electrons in CH2Cl2, we get 20 electrons. Okay, so that's step 1. We've completed step 1. We've counted all of our valence electrons. Next up, we want to draw our skeletal structure with bonds between the central atom and the surrounding atoms. Well, remember, we read from left to right, so our central atom is carbon, and the atoms that surround it are going to be 2 hydrogens and 2 chlorines. Okay, remember this is like a box, so they can go on either side. Since there's 4 atoms in total, they fit on all 4 sides. And then we're going to connect those surrounding atoms to our central atom with bonds. So that was step 2. Step 3 says to subtract the bonded pair electrons from the total number of electrons. So I had 20 electrons total. How many electrons did I use to make those bonds? Well, each bond has 2 electrons in it, and if I made 4 bonds, I used up 8 electrons. So I have 12 electrons left over. So we finished step 3, and now we can move on to step 4, where we place remaining electrons. So I have 12 remaining electrons that I'm going to place as lone pairs on my surrounding atoms to complete their octets. So hydrogen does not need any lone pairs because it already has 2 electrons associated with it, and that completes its duet, so it's happy. So hydrogens are happy. The chlorines, on the other hand, only have 2 electrons associated with it, so we need more electrons to complete its octet, specifically 6 electrons. So we can put those as lone pairs, 1, 2, 3, 4, 5, 6 on the chlorine. That way when I look at this chlorine, it has 8 electrons. Okay, the same can be done to the other chlorine, 1, 2, 3, 4, 5, 6. And if we do that, then it has 8 electrons. So putting on those lone pairs, I used up 1, 2, 3, 4, 5, 6 pairs of electrons, which is 12 electrons. So I have no more electrons left. So step 5 doesn't apply because I don't have any electrons remaining. The last thing we are going to do is just double check our octets. Well, we already said that chlorine had its octets and hydrogen has its octets. We just have to double check that carbon also has its octet, and it has 4 bonds to it. Those 4 bonds in total have 8 electrons, so carbon also has its octet. So That is our Lewis structure for CH2Cl2. Let's practice another one. Our next practice had us doing NH3. So let's do NH3. Okay. So our first step is to count our valence electrons. So our valence electrons of nitrogen is 5 because they are in group 5. We're going to add to that, we have 3 hydrogens, each with 1 valence electron. So that's a total of 3 electrons from hydrogen. So in total we have 8 valence electrons that we are using to create the structure. So that's step 1. Step 2 was our skeletal structure. We put our central atom and put our surrounding atoms around it. So our central atom is nitrogen, and the surrounding atoms are hydrogen. Those 3 hydrogen. I don't have any more hydrogen. So even though we treat it like a box, if I don't have enough to go around, that's fine. I'm putting it on 3 of the 4 sides. Okay. So then I connect my surrounding atoms to my central atom with bonds. I now subtract the number of electrons I used to make those bonds from my total. So I used up 1, 2, 3, 4, 5, 6 electrons to make those bonds. So I'm subtracting off 6 electrons. And I have 2 electrons left. So step 4 tells us to place remaining electrons as lone pairs to complete octets or duets. Since our surrounding atoms are all hydrogens and they all have their 2 electrons associated with them, right? These 2 electrons go to that carbon, these 2 electrons go to that carbon, or hydrogen I should say, sorry, and those 2 electrons go to that hydrogen. They all have their duets, so all of those hydrogens have their duets and they're happy. So we've completed step 4 without having to place any remaining electrons anywhere. So we still have 2 electrons left. So we move on to step 5, which says place any remaining electrons after our octets are complete on surrounding as pairs on the central atom. So our central atom here is nitrogen. If we look at it as it is right now, it only has 6 electrons, right? It has 3 bonds associated with it, and those bonds all have 6 electrons in it, so it doesn't have an octet yet. But I have these 2 electrons that I can place as lone pairs on there. So I've placed those. I'm going to subtract those 2 electrons off because I've used them, and I have no electrons left. And now, since I placed those, I now have an octet on my nitrogen, okay, meaning my nitrogen also has its octet. So everything has an octet or a duet, and it's completely happy. So that is our structure for NH3. Okay, our last example was CH2O. So let's do CH2O. Step 1, count our valence electrons. We know that carbon has 4 valence electrons. We then have 2 hydrogens that each contribute 1 valence electron. And then oxygen has 6 valence electrons. Oxygen has 6 valence electrons in total. So altogether we have 12 electrons that we can use to draw our structure. Okay, our central atom is then going to be carbon with 2 hydrogens around it, as well as an oxygen. So we're just reading from left to right. So we see our central atom is carbon, 2 hydrogens, and an oxygen surround it. And we're going to connect those surrounding atoms to our central atom using bonds. Because I made 3 bonds, I used up 6 electrons, okay, because each bond has 2 electrons in it, meaning I have 6 electrons left. Step 4 tells us to take those remaining electrons and place them on our surrounding atoms as lone pairs to complete octets. Well, hydrogens don't need them. They all had their duets, so they're happy. Our oxygen only has 2 electrons, so we're going to do 1, 2, 3, 4, 5, 6 electrons to complete its octet. Okay, right? It has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. So because I placed those 6 electrons on oxygen, I have no electrons left. Okay, try to erase this because I need that to be clear. Let me redraw my carbon here. Okay, so now we want to double check our octets. Well, we said the hydrogens both have their octets. We also said the oxygen now has its octet. And if we look at carbon, it only has 3 bonds, meaning those 3 bonds only associate with 6 electrons. So carbon does not have its octet. So let's go to our rules. And step 6 says if octets are not complete, form multiple bonds by moving electron pairs. Okay, so we have to create a multiple bond, and we have to do that by moving electron pairs. So what I'm going to do is say that these 2 electrons from oxygen, that's an electron pair, okay, those can be shared with carbon. Oxygen's going to say, well, I already have these 2. If I just give them to you in the form of a bond, I'm still claiming those, I'm still maintaining my octet, but that means you also have an octet. So oxygen's just being very polite and is allowing more electrons to be shared. So what that does is it creates a double bond. So C, H, H. We have an O. One bond was made from the beginning, and I'm going to do a different color to show this, that purple bond was made from moving those lone pairs. Okay, so we made a double bond, and we can now check. Well, we know our hydrogens have their octets. Oxygen now has 2, 4, 6, 8 electrons, so it has its octet. And carbon now has 4 bonds around it, meaning it has its octet. So by moving one pair of electrons, we are creating a double bond, and then that's completing our octet for carbon. We only move lone pairs to create multiple bonds if octets are not complete. Okay, I wouldn't move this lone pair anywhere on this nitrogen just because it was there. Okay, I wouldn't do that because all of my octets were complete. The only reason we moved these lone pairs in the first place was because carbon did not have an octet. So only do step 6 if octets are not complete. I oftentimes see students saying, well, I have these lone pairs, I could just make double bonds, but if my octets are already complete, the molecule doesn't want to form any double bonds. So just because you have lone pairs does not mean that you should form multiple bonds. Okay, you only form double bonds or triple bonds if octets are not complete. So we have to check our octets. That's why it's the very last step. Okay, let's keep on practicing. Keep on doing it. We're going to practice these until we master them. So, next up we have H2O. That's water. We've seen the water one before, but we're going to prove it now. We've been shown the Lewis structure. Now we're going to prove it to ourselves. So we have H2O. Hydrogen has 1 valence electron, but there's 2 of them. And we're going to add to that the 6 valence electrons of oxygen. That gives us a total of 8 electrons. Now here's a case where hydrogen is not going to be our central atom. Remember I said if hydrogen comes first, it is not the central I'll write it again. Hydrogen will never be central atom. Okay, so oxygen is going to be our central atom here, and it's going to be surrounded by our hydrogens, which we're going to connect with bonds. I'm just going to move this over. Okay, so because I made 2 bonds, I used up 4 electrons. So I have 4 electrons remaining. My next step tells me to take any remaining electrons and place them on my surrounding atoms to form octets. Okay, hydrogen has 2, hydrogen has 2, they're happy, so step 4 is done. We move on to step 5, which says place any remaining electrons on the central atom to complete its octet. So we have 4 remaining electrons. Oxygen only has 4 electrons surrounding it right now. So these excess 4 electrons are going to be placed on the oxygen as lone pairs to complete its octet. So now, in total, it has 8 electrons. 2 from the lone pairs, 2 from the bond. 4 from the lone pairs, 4 from the bonds. Okay. So that's our structure of water. That was the Lewis structure that we've been looking at all through this lecture, and we've just proved it, that is definitely what it looks like, and that's how we derived it. Our next example is O2, which is molecular oxygen. Okay, so O2 has 6 valence electrons, but there's 2 of them. So we have a total of 12 electrons to draw the structure. Since there's only 2 atoms in this molecule, those oxygens are just going to be next to each other. There is no one central atom. So my 2 oxygens are bound together by a single bond. My single bond used up 2 electrons. So I have 10 electrons left. So the rule then says any remaining electrons should be placed around the atoms to complete octets as lone pairs. 4 and 5, the difference between them is a little bit hazy right now because we don't have a central atom versus surrounding atoms. So we're just going to take these remaining 10 and place them on our oxygens. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I used up all 10 electrons and I have none left. So our next step is to check octets. This oxygen has 3 lone pairs and a bond, so it has 8. Okay, so that has its octet. This oxygen has 2 lone pairs and a bond, so that's only 6 electrons, so it does not have its octet. So if octets are not complete, we need to take lone pairs and we need to share them to create multiple bonds. So remember, we only create double bonds if octets are not complete. This oxygen has an incomplete octet. It does not have enough electrons around it. So the oxygen that does have 8 electrons around it is just going to share one of those pairs of electrons in order to create a multiple bond. So this becomes oxygen bonded to oxygen. This oxygen still has 2 lone pairs. This oxygen now has 2 lone pairs, because its 3rd lone pair is now shared in between the oxygens with a double bond. So we can double check. This oxygen now has 8 electrons around it, and this oxygen now has 8 electrons around it. Okay, so another one where we had an incomplete octet. So we had to share electrons and create a double bond. Okay. Our next example, or our last one for this slide, is CCl4. CCl4. So we have carbon first. Carbon has 4 valence electrons. Then we have chlorine. Chlorine has 7 valence electrons because it's in group 7A, but there's 4 of them, so we take 4 times those 7 valence electrons. So in total, I have 32 electrons. Again, feel free to type these things into your calculator and double check. It's always useful to double check. Doesn't hurt. So we have 32 electrons that we are going to share amongst this entire molecule. So we start with carbon in the middle. That's our central atom because it comes first. And it's surrounded by 4 chlorines, which we're going to bond to the carbon with bonds. So I made 4 bonds, which means I used up 8 electrons because each bond has 2 electrons in it. So after making bonds, I have 24 electrons left. So my next step says to take any remaining electrons and place them on my surrounding atoms to complete octets. We can see that each of our chlorines only has 2 electrons, so they all need an additional 6 electrons to complete their octets. So let's see if we have enough electrons to do that. So we're going to place them as lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I used up all 24 of my electrons to complete the octets of my chlorines. So all of my chlorines have their octets. Let's just double check that our carbon has an octet. It has 4 bonds around it, which means it has 8 electrons that are surrounding it because we have 4 bonds. Each bond has 2 electrons. That's a total of 8 electrons. So carbon also has its octet, and that is our finalized Lewis structure. Okay, let's do a few more. What I want you to do is I want you to try these on your own. It's okay if you mess up. Okay, remember the point of trying these on our own is to get stuck and then use our videos to get unstuck so that we learn the topic even more. So I have 3 examples here that follow the same rules that we did before. Okay, so keep using those rules, get used to using those rules for drawing Lewis structures, and try these 3 on your own. The one comment I will make is about OCS, our last example here. I made the note that carbon is the central atom, so it is a carbon with a sulfur and an oxygen on either side. So that's your starting structure for what you're going to draw. So try drawing these Lewis structures, pause the video, and come back when you're ready to check your work. Okay, let's start off with our first example here. We have NCl3. So let's count up our valence electrons. Nitrogen has 5. Chlorine, there's 3 of them, and they each contribute 7 electrons. So in total, we have 26 electrons to place in this molecule. Nitrogen is our central atom here, and it's surrounded by chlorines, which we bond to the nitrogen with single bonds. I made 3 bonds, so I used up 6 electrons. Each bond has 2 electrons in it. So in total, I have 20 electrons left. My next step says to complete my octets of my surrounding atoms by placing my excess electrons as lone pairs. So all of my chlorines only have 2 electrons right now. They need another 6. So let's use some of these 20 electrons to complete our octets. So I have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I used 18 electrons to complete my octets of chlorine. I have 2 electrons left over. Well, we can see that my nitrogen does not have a complete octet. It has 6 electrons around it. It needs 2 more. So we're going to take those 2 electrons and place them on the nitrogen to complete its octet. I've used up all of my electrons, and that is now my completed Lewis structure of NCl3, where everything has an octet. My next example is OF2. Okay, oxygen, let's count up our valence, has 6 valence electrons. Fluorine, there's 2 of them. We're going to multiply it by the 7 valence electrons in each fluorine for a total of 20 electrons in this structure. Oxygen is our central atom with fluorines around it that we connect to the oxygen with bonds. I made 2 bonds, so I had to use 4 electrons to create those bonds. So I have 16 electrons left over. I'm going to use those 16 electrons to complete the octets of my surrounding fluorines, because each fluorine right now only has 2 electrons. So they each need 6 more. So I do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I used 12 electrons to complete the octet of my fluorines, and I'm left with 4 electrons left. My fluorines both have their octets, but my oxygen does not. I only have 4 electrons around the oxygen right now. So step 5 tells us to use any remaining electrons and place them as lone pairs on the central atom to complete its octet. I put 2 lone pairs on the oxygen to complete its octet. That used up my last 4 electrons. I have no electrons left, and everything now has an octet in my structure. So that is my structure of OF2. My final example is OCS, where the carbon is the central atom here. So let's count up our valence electrons. I have 6 from the oxygen, 4 from the carbon, and 6 from the sulfur. So that's a total of 16 electrons in my structure right now. So if carbon was central, we had carbon that was bound to a sulfur and an oxygen. That used 4 electrons right there to create those bonds. So I have 12 electrons left. Those 12 electrons are going to be placed around my sulfur and my oxygen, since they both have incomplete octets. They only have 2 electrons, so they each need 6. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I used all 12 remaining electrons to complete the octets of my surrounding atoms, and I have no more electrons left over. But my carbon is missing 4 electrons. It only has 4 electrons right now. It needs 4 more. So what we're going to do is take some pairs from our sulfur and our oxygen, and we are going to create multiple bonds. So, like we've seen before, oxygen will give up one of its lone pairs to create a bond, and since sulfur and oxygen are in the same group, they're going to have similar properties. So if oxygen is polite and donates a lone pair, sulfur will also be polite and donate a lone pair. So this now creates a structure of OCS. Those now have double bonds, and I'm now 2 lone pairs on my sulfur and my oxygen. That doesn't change my octet because the oxygen still has 8, the sulfur still has 8, and the carbon now has 8. So my final structure of OCS is O double bond C double bond S, with oxygen and sulfur both having 2 lone pairs. So that's my final structure. Okay, let's move on to something a little bit more tricky. What if we had 2 central atoms? Our rules don't really change much for if I have multiple central atoms. We still count up our valence electrons and everything and do our steps the same way. It's just now we have 2 central atoms to count and double check that we have octets for. So let's start off with H2O2, our first example. Remember, hydrogen cannot be our central atom, so oxygen is going to be central. So for H2O2, we're going to count up our valence electrons. I have 2 hydrogens, which each contribute 1. I'm going to add to that my 2 oxygens that each contribute 6. So I have a total of 14 electrons in H2O2. My oxygens are now my 2 central atoms, meaning that they are going to be bonded together. Okay? And each of those oxygens are going to have hydrogens coming off of it. Okay? What I can't draw is the hydrogen bonded to a hydrogen with an oxygen and an oxygen, because remember, this hydrogen now has 2 pairs, or 2 bonds. This hydrogen now has 2 bonds, and hydrogen will only bond once. So this will not be our structure. So let's just erase that out of our minds. Hydrogen will never make more than 1 bond. Okay, so that's our structure. I've used up all of my atoms. And in doing that, I've used up 6 electrons, right? I have 2, 4, 6 electrons that are wrapped up in bonds. So I'm going to subtract those 6 electrons there. And I'm going to be left with 8 electrons left over. So my rule says to place my extra electrons on my surrounding atoms to create octets, but my surrounding atoms are hydrogens and they both have a bond to them, so they are happy with their duets. So my next step says to take any remaining electrons and place them on the central atom, or in this case atoms, to create their octet. So I have 8 electrons here. Each oxygen right now has 4 electrons, so they each need 4 more electrons to complete their octets. So let's take these 8 electrons and place them on our central atoms. So I placed all 8 electrons on my oxygens. I have no electrons left over, but if we look at our octets, that oxygen now has a complete octet, as does that oxygen. So that is our completed structure for H2O2. Our next example is N2F2. Okay, nitrogen, the 2 nitrogens are going to be our central atoms. So I have 2 nitrogens that each contribute 5 valence electrons, and I have 2 fluorines that each contribute 7. So in total I have 24 electrons. My nitrogens are going to be my central atoms. I'm going to bind them together with a bond, and they each have a fluorine coming off of them. So again, I've made 3 bonds, so I've used up 6 electrons. So I have 18 electrons left over. My fluorines have incomplete octets here, so I need to use some of these electrons to complete their octets. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I used 12 electrons to complete their octets, so I'm left with 6 electrons left over. Step 5 of our guidelines says to replace any remaining electrons on our central atoms as lone pairs. Okay, so I'm going to say 1, 2, 3, 4, 5, 6. We're not going to separate those electrons up or anything. We're going to keep them as lone pairs. I've used them all up. I have no electrons left. Our last step is to just double check that everything has an octet. We know our fluorines have octets. My first nitrogen here has an octet, but my second nitrogen here does not. My nitrogen does not have a lone pair. Does not have an octet. So we're going to have to move a lone pair of electrons in order to form a double bond so it can have an octet. Now, because we have multiple central atoms here, we have some choices. So the fluorine could donate its 2 electrons there. We can create a double bond between the nitrogen and the fluorine. Or we could use the nitrogen on the other side that has 2 lone pairs, and it can now form a double bond in between that nitrogen. So we have some choices, but our choices can be changed if we remember some rules about specific atoms. So some rules about certain atoms. The first one, hydrogen will only bond once. The second one, halogens prefer to only bond once. Can they bond more than one time? Yes, if it's the only option, but if there is another option, then it will not bond more than once. So halogens prefer to bond only once. Oxygen likes 2 bonds and 2 lone pairs, which we may have been seeing as we have been drawing structures with oxygens. Okay, it has 2 bonds and 2 lone pairs. And carbon likes 4 bonds, no lone pairs. So carbon would prefer to have all bonds and no lone pairs at all. And finally, nitrogen likes 3 bonds and one lone pair. Okay, so oxygen likes 2 bonds, 2 lone pairs, nitrogen likes 3 bonds, 1 lone pair, and carbon likes 4 bonds, no lone pairs. You'll notice that they are in a specific order on your periodic table that expresses that, because halogens prefer to only bond once, and that means that they have 3 lone pairs. Okay, so if we look at our options here, if I were to do this first option, that would mean that my fluorine would have a double bond. It would have 2 bonds and 2 lone pairs, which is not what it prefers. If I use my second option, I would have a double bond between my nitrogen and my 2 nitrogen. Each nitrogen would then have 3 bonds and 1 lone pair, which is what it prefers. So we are going to go with option 2. Okay, so we follow just our general rules about certain atoms, and we say that the preferred structure would be, I'm going to draw this clearer down here, F, N, double bond N with an F. I have 2 lone pairs on my nitrogen, 3 lone pairs on all of my fluorines, and everything has an octet, and this structure follows my rules of certain atoms. Are there exceptions to these rules? Yes, we will see this oftentimes with larger molecules, if they just have a lot more electrons. We also see it if we have charges, that these rules can change. But typically, for neutral atoms, If they're not too large of atoms, okay, they will follow these general rules. Hydrogen will only bond once. Halogens will also only bond once and have 3 lone pairs. Oxygen will bond twice and have 2 lone pairs. Nitrogen will bond 3 times and have 1 lone pair, and carbon will have no lone pairs and only bond 4 times. Okay, those are our general rules of specific atoms that we see often. Okay, so our final structure for NF2 is down here. We just have to make a decision about where our double bond would go. That appeases our rules. Okay, let's look at our last example. Si2H6. So, Si, let's count up our valence electrons. Silicon has 4, and there's 2 of them. So there's 2 silicon atoms. Each atom has 4 valence electrons. We're going to add to that our 6 hydrogens, which each have 1 valence electron, and that is a total of 14 electrons that we're working with in this structure. I'm just going to draw a line down the middle here. Okay, so silicon is our 2 central atoms. We're going to bind those together to each other, and then they each have, what we can't tell is we have 6 hydrogens in total. Remember, this is like a square. Okay, so each of these is going to have a hydrogen on either side of it to complete its square. Okay, so hydrogen, hydrogen. I'm going to remove that square so that we can easily see our bonds. Okay, so I've made my bonds. Let's count how many bonds I made. 1, 2, 3, 4, 5, 6, 7. I made 7 bonds. Each bond has 2 electrons in it, meaning I used up 14 electrons. I'm going to subtract off 14 electrons. I have no electrons left over, so let's double check our octets and our duets. Well, hydrogen all have 2, so they're all happy. Each silicon has 4 bonds to it. 4 bonds means 8 electrons, meaning it has octets. So that is our final structure of Si2H6. Okay. Whew, that was a lot of Lewis structures. And don't worry, we have more moving on in this lecture. But I do want to just make a note about Lewis structures of ions. We've talked about ions a lot in our course so far, so we're going to talk about them a little bit more. So we can also write Lewis structures of ions. We can follow the same steps. We just have to account for the change in number of electrons in our first step, because the definition of an ion is that it has either accepted or removed electrons. So we have to account for that change in number of electrons. And in our first step, we're counting the valence electrons. So let's do the example of OH minus. This is hydroxide. That's one of our polyatomic ions. So let's see, count up our valence electrons, and for ions, also account for the charges. Well, this is OH minus. The minus means I've added 1 electron, right? Minus 1 means I have 1 more electron than proton. So we count up for OH minus. We say that oxygen has 6 valence electrons, hydrogen has 1, and I'm going to add my 1 extra electron. That one's coming from my charge. So in total, I have 8 electrons that I'm using to draw this structure. Okay, so let's draw our structure. We have O bound to an H. I used up 2 electrons to draw that bond. I have 6 electrons left. I'm going to place that on my atoms to complete their octets. Hydrogen has a duet, so it's happy. So those 6 electrons are going to go on the oxygen. I have no electrons left, and that oxygen now has an octet. So that is our final structure of OH. Now, when we're drawing our Lewis structures of ions, we have to represent the ion in the Lewis structure in some way. So what we're going to do is surround the structure in brackets and put the charge on the outside of those brackets. Okay, so the charge on OH minus was -1, so I put a minus on the outside there. If this was -2, you would put a -2. If this was a +3, you'd put a +3. Okay, so when you note your charge on the outside of your Lewis structure, you want to put it on the brackets because that electron is being shared amongst the entire atom. If I didn't have the brackets, let me erase them really quick. If I didn't have these brackets and I just put them here, it would look like the electron was on the hydrogen, which it technically isn't because the electron, that extra electron from the charge, is being shared amongst the entire molecule. Okay, so we put our brackets around it with the charge on the outside. Okay, let's do a few more. Now, what I want you to do with these is get used to accounting for the charges. So before we go into drawing the Lewis structures, what I want you to do is for each of these examples, count up the total number of electrons in the molecule, properly accounting for the charges. Okay, so remember, if it's negative, we add electrons. If it's positive, we remove electrons. So pause your video for a second and try that just to get used to counting up the total number of electrons for each of these ions. For our first example, NH4+, we're going to count up our valence electrons as is. So we're going to say nitrogen has 5. Hydrogen contributes 4, right? That's 1 times 4. And since we have a plus charge, it means we removed electrons. How many electrons did we remove? Well, there's no number next to it, so it's 1. So we subtract 1. So we get total number of electrons in the structure as 8. In ClO3-, we have Cl, which has 7. We have oxygen, there's 3 of them, and each oxygen has 6 valence electrons. It has a minus charge, so we have to add an extra electron. That's a -1, so we're adding 1 extra electron. You'll notice that these charges are essentially allowing us to not have an odd number of electrons, because if we had an odd number, then we wouldn't have enough to make pairs. Okay, and everything likes to be paired up. So these charges are useful for making sure that we have enough electrons to be paired up. Okay, for HCOO-, we have 1 from the H, 4 from the carbon, 12 from the 2 oxygens, and 1 extra because it's a minus charge. So in total we have 18 electrons. And then Cn-, we have 4 from the carbon, 5 from the nitrogen, plus 1 extra because it's a 1-. So we end up with 10 electrons. So let's start drawing these. Now that we have our total number of valence electrons, we follow our steps as is. So here we have NH4. We have N as our central atom. It's now surrounded by 4 hydrogens, and each of those will be a bond. Okay, so in making those bonds, I used up 2, 4, 6, 8 electrons. I have no electrons left. My hydrogens all have octet or duets. My nitrogen now has an octet because it has 4 bonds around it. So the last thing I have to do is surround this with a bracket and put my charge. So that is my structure for NH4+. So this is one of those exceptions to our rule about nitrogen. Again, we said it usually happens when there's an ion involved, so nitrogen is bonding 4 times. It's only allowed to do that because of the positive charge. Okay, let's try ClO3-. Let's see, we have Cl as our central atom. We have O's that surround it with bonds. So I've used up 6 electrons. I have 20 left. I'm going to use those 20, 2, 3, 4, 5, 6. I'm putting those on my oxygens to complete their octets. Okay, each oxygen only had 2. Now with their complete octets, or now with their lone pairs, I've completed their octets. I used 18 electrons to do that, so I have 2 electrons left. Those 2 electrons are going to go on my chlorine to complete its octet, right there. So now that everything has an octet, we're just going to surround this with brackets and put our charge on the outside. So we're following the same steps that we did in all of our previous Lewis structures, except now we are going to be representing our charge with brackets. Okay, next up we have HCOO. Here, hydrogen cannot be central. Carbon is going to be central, so it's the one that comes after the hydrogen. That's going to be surrounded by an oxygen, and a hydrogen. So I've used up 6 electrons to do that. I have 12 left. Okay, I'm going to place my extra electrons as lone pairs. I put them on the oxygens because the oxygens needed octets. My hydrogen did not, it had a duet already. So I've used up all 12, they're all gone, but my carbon does not have an octet. So since I have no electrons left and I need to complete my octet, I'm going to take one of my lone pairs of my oxygens, I'm going to place it on my carbon to get a final structure of a double bonded O to that carbon. Now everything has a duet, my oxygens, and now my carbon. So the final thing is place brackets around it and throw a negative sign on there. Our last example is Cn-. This is a good one. So we have C bonded to N. I used 2 electrons to do that. I now have 8 electrons left. So let's take those 8 electrons. Let's say 1, 2, 3, 4, 5, 6, 7, 8. Well, I used up all 8 electrons, making my lone pairs, but now my nitrogen only has 4 electrons around it. So, carbon is going to donate one of its lone pairs there. So we're going to end up with C double bond N. That lone pair stays on that nitrogen. I then have my carbon double bonded with 2 lone pairs. But you'll notice that moving that, I now only have 6 electrons on my nitrogen. Let's see if there's more I'm going to do. So I don't have a complete octet yet. So what we're going to do is take another lone pair from carbon and move it down there. And we get C triple bond N with a lone pair on the nitrogen and a lone pair on the carbon. Okay, so nitrogen is still having three bonds and a lone pair. Carbon, not so much, but that's because we have an ion. So that's how we make triple bonds. By making a double bond, I didn't complete my octet, so I had to move another pair of electrons to make a triple bond. Okay, so that's our structure for Cn-. Okay. Let's look at these structures a little bit differently. So currently in these 3 structures, something is wrong with them. So let's try to figure out what is wrong. You're going to see similar problems to this on your ALEKS homework. So the first thing that we're going to want to do is count our valence electrons. And double check they're all there. And then our second thing is going to be to check our octets. Okay, so if we have C and N, we have carbon has 4, Nitrogen has 5. There's a minus charge on there, so that's 10 total electrons. Let's count up our electrons in this structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have all 10 electrons. So now let's check our octets. My carbon only has 6 electrons. My nitrogen has an octet. So the something wrong with our structure is that carbon has incomplete octet. That was just like one of our structures that we drew on our previous slide. We had a double bond and we needed another bond to complete our octet. Okay, let's look at our next one. We have CO. So carbon has 4, oxygen has 6. There's no charge, so in total we should have 10 electrons in this structure. Let's count our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we do not have 10. So the issue with this structure is we have too many electrons. So we have 12 electrons total, but there should only be 10. Okay, let's do our next example. We have NOCl. Nitrogen contributes 5, oxygen contributes 6, and Cl contributes 7 valence electrons for a total of 18. Let's count up all of our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All of our electrons are there. So let's just double check our octets. Chlorine, that has an octet. Oxygen, that has an octet. So let's check our nitrogen. Nitrogen does not have an octet. So nitrogen has an incomplete octet. It's missing 2 electrons. Okay. Let's practice a little bit more. Let's try to identify the correct Lewis structure of carbon dioxide. Now we can do this a couple of different ways. We can go through each structure in our multiple choice options here and we can figure out what's wrong with them. Or we could draw carbon dioxide using our rules and see which one matches up. You can do it either way. First off, we should always just double check our number of valence electrons. So carbon dioxide is carbon oxide 2. Remember, di is 2. So there's 1 carbon, 2 oxygens. So in total we should have 4 plus 2 times 6. So we have 16 total electrons. Let's see if we can knock out any of these structures by counting electrons. Let's see, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This one has too many electrons. Okay. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That one's valid. Okay. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That one does not have enough electrons. This one has 1, 2, 3, 4, 5, 6, 7, 8. Not enough electrons. And this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Again, too many electrons. So this one had 16 electrons. Great, it's our only one left. But we can double check and keep practicing drawing our Lewis structures. So we know that there are 16 electrons in total. Carbon is our central atom that's bound to 2 oxygens. So that used up 4 electrons. So I have 12 left. Those 12 are going to go on my oxygens. Okay. That used up all 12 electrons, so I have none left. We see that our oxygens all have octets. but our carbon does not. So each oxygen is going to be nice and donate a pair of electrons. Since the carbon needs 4 more electrons, those 4 electrons are coming from the 2 lone pairs. So we get O, double bond C, double bond O, with 2 lone pairs on either oxygen, which corresponds to structure D. So we have multiple ways that we can double check it. The first one is right off the bat, just count your electrons. Make sure that none of those have too many electrons or too few, and then double check with your own rules. Okay. On our last set of problems here, what I want you to do is pause the video and try to figure out what's wrong with these. Using our steps of first, count your valence, and check the molecule, and then check octets. So pause the video, use our 2 rules for each of these compounds to double check and see what is wrong with each structure. In our first example, we should count up our valence. So hydrogen, there's 2 of them, so that's 2 valence, plus the 6 in oxygen, that's a total of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, so they're all there. But our big thing that's wrong is that hydrogen can't bond twice. Okay, it wants a duet. It means 2 electrons. So that's what's wrong with our first structure. For our second structure, we have to count up our valence. So we have 4 from the carbon, 14 from the chlorines, and 6 from the oxygen. So in total, that's 24 electrons. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So we have too many electrons. Okay. And finally, in our last structure, we have Cl, which has 7, plus 6 from the oxygen, but there's a minus charge, so we have to account for 1 extra electron. So I should have 14 electrons in this structure. Right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm missing electrons. I have too few electrons, not enough electrons in my structure. So that ends our lesson on Lewis structures. Keep practicing these, get used to utilizing those rules. I definitely suggest making sure you can go through the entirety of the ALEKS homework and complete all of those problems and drawing those structures before moving on to our next lesson, which takes our Lewis structures and now we apply them. We do a few more exceptions and stuff like that. So we have to be able to master our Lewis structures first before moving on. So make sure you complete your ALEKS homework and fully understand Lewis structures before moving on to our next lesson.